In numerical analysis, the speed at which a convergent sequence approaches its limit is called the rate of convergence. Although strictly speaking, a limit does not give information about any finite first part of the sequence. This concept is of practical importance if we deal with a sequence of successive approximations for an iterative method, as then typically fewer iterations are needed to yield a useful approximation if the rate of convergence is higher. This may even make the difference between needing 10 or a million iterations insignificant. Similar concepts are used for discretization methods. The solution of the discretized problem converges to the solution of the continuous problem as the grid size goes to 0, and the speed of convergence is one of the factors of the efficiency of the method. However, the terminology in this case is different from the terminology for iterative methods. Series acceleration is a collection of techniques for improving the rate of convergence of a series discretization. Such acceleration is commonly accomplished with sequence transformations. Convergence speed for iterative methods. Basic definition: suppose that the sequence xk converges to the number L. We say that this sequence converges linearly to L if there exists a number mu such that the number mu is called the rate of convergence. If the sequence converges, and varies from step to step with φ, then the sequence is said to converge superlinearly. Varies from step to step with φ, then the sequence is said to converge sublinearly. If the sequence converges sublinearly and additionally, then it is said the sequence xk converges logarithmically to L. The next definition is used to distinguish superlinear rates of convergence. We say that the sequence converges with order q to L for q greater than 1 if in particular, convergence with order q equals 2 is called quadratic convergence, q equals 3 is called cubic convergence, etc. This is sometimes called q-linear convergence, q-quadratic convergence, etc., to distinguish it from the definition below. The q stands for quotient, because the definition uses the quotient between two successive terms. Extended definition: the drawback of the above definitions is that these do not catch some sequences which still converge reasonably fast, but whose speed is variable, such as the sequence bk below. Therefore, the definition of rate of convergence is sometimes extended as follows. Under the new definition, the sequence xk converges with at least order q if there exists a sequence epsilon k such that and the sequence epsilon k converges to 0 with order q. According to the above simple definition, to distinguish it from that definition, this is sometimes called our linear convergence, our quadratic convergence, etc. Examples: consider the following sequences. The sequence A converges linearly to 0 with rate 1/2. More generally, the sequence C mu k converges linearly with rate mu if mu less than 1. The sequence bk also converges linearly to 0 with rate 1/2 under the extended definition, but not under the simple definition. The sequence ck converges superlinearly. In fact, it is quadratically convergent. Finally, the sequence dk converges sublinearly and logarithmically. Convergence speed for discretization methods. A similar situation exists for discretization methods. The important parameter here for the convergence speed is not the iteration number k, but it depends on the number of grid points and grid spacing. In this case, the number of grid points n in a discretization process is inversely proportional to the grid spacing. In this case, a sequence is said to converge to L with order p if there exists a constancy such that this is written as xn L equals O using the big O notation. This is the relevant definition when discussing methods for numerical quadrature or the solution of ordinary differential equations. Examples: the sequence dk with dk equals 1 was introduced above. This sequence converges with order 1 according to the convention for discretization methods. The sequence ac with ac equals 2 minus k, which was also introduced above, converges with order p for every number p. It is said to converge exponentially using the convention for discretization methods. However, it only converges linearly using the convention for iterative methods. The order of convergence of a discretization method is related to its global truncation error, acceleration of convergence. Many methods exist to increase the rate of convergence of a given sequence, i.e., to transform a given sequence into one converging faster to the same limit. Such techniques are in general known as series acceleration. The goal of the transformed sequence is to reduce the computational cost of the calculation. One example of series acceleration is Aitken's delta-squared process. Literature. The simple definition is used in Michel Schatzman, Numerical Analysis. A Mathematical Introduction, Clarendon Press, Oxford. ISBN 0-19-850279-6. The extended definition is used in Kendall A. Atkinson, An Introduction to Numerical Analysis, John Wiley & Sons. ISBN 0-471-50023-2. http://web.mit.edu/ruden/www/mcurgerisk11col.pdf. Walter Gautschi, Numerical Analysis. An Introduction, Berkhauser, Boston. ISBN 0-8176-3895-4. Endra Sully and David Mayers, An Introduction to Numerical Analysis, Cambridge University Press. ISBN 0-521-00794-1. Logarithmic convergence is used in Van Tuyl, Andrew H. Acceleration of convergence of a family of logarithmically convergent sequences. Mathematics of Computation 63. 229-246. DOI 10.2307, 2,153,571. The Big O definition is used in Richard L. Burden and J. Douglas Fair's Numerical Analysis, Brooks, Cole. ISBN 0-534-38216-9. The terms Q-linear and R-linear are used in the Big O definition when using Taylor series as used in Nossedal, George, Wright, Stephen J. Numerical Optimization. Berlin, New York. Springer Verlag. pp. 619+620. ISBN 978-0-387-30303-1. One may also study the following paper for Q-linear and R-linear. Potra. A. On Q-order and R-order of convergence. J. Optum. Th. APPL. 63. 415-431. DOI 10.1007, BF009399805.